All right, last time we were working in section 1.4, which is about continuity and one-sided limits. One-sided limits had the field where we had these addition or subtraction signs afterwards. And we've encountered them before, but now we're looking at them from an algebraic standpoint and from the fact that we can evaluate as the number 8 as long as it doesn't make things like zeros in the denominator. We have the ability to do that. So I believe that we had gotten to discontinuities. Are we right here? Does that look right? Okay. All right, so if a function's not continuous, there are two different types, like categories, of discontinuities. One type of discontinuity is called removable. This occurs when f can be made continuous by appropriately defining or redefining f of c. Visually speaking, this happens when there's a hole in the graph. And holes in the graph typically occur when we have the ability to factor and reduce something. Those are kind of key ideas. A non-removable discontinuity occurs when f cannot be made continuous by appropriately defining or redefining f of c. And this typically happens when there's an asymptote. So let me kind of draw a picture of each of these so you can see why they're different and talking about this defining and redefining. So if you have my visual of a hole in the graph, then it means at this particular point there's a discontinuity, right? Yeah, because there's a hole in the graph. But if you were able to sort of fill in the hole in the graph and define that that point is going to equal whatever that y value, where the hole in the graph is, it would then be continuous, right? So you have the ability to fill in the hole. That's different than if you have an asymptote. If you have an asymptote, we'll draw it that way. There's no way to fill in the gap of the asymptote, right? There's no hole to fill in. I can't just say, oh, look, it's going to be here. It still would be discontinuous. There's no way to connect one side to the other side at a particular value. So that's called a non-removable discontinuity. So what we're going to take a look at is we're going to take a look at some functions and deciding whether or not the discontinuity is removable or non-removable. So this one starts out by asking you what x values is it not continuous for, and is it removable or not removable? That's really the question. Which of the discontinuities are removable? So what x value are you not allowed to have here? Yeah. So there's a discontinuity. So it's discontinuous at x equals 0. And you know what's happening at that value, because this is not an unfamiliar function to you. What's happening at 0 on this? Is it a hole or is it an asymptote? It's an asymptote. And if you aren't sure on this function or some other function, you can always graph it, right? So the basic graph of this function looks something like this. It has an asymptote at the y-axis. So that makes this discontinuity non-removable, right? So this is a non-removable discontinuity. And I would write yourself a note that says this is because there's an asymptote there. So it's an asymptote at x equals 0 is the equation of that asymptote. So if you have an asymptote, you have a non-removable discontinuity. Okay? The next function is a little bit more complicated because there's more going on in it, right? There's just more pieces. So how would I figure out what x values here I'm not allowed to have? That is where the discontinuities occur. What's that?
Like perfect square factoring.
Okay, so we would do something with factoring, right? We would like to factor the denominator in particular because the denominator is going to be the locations where I potentially have discontinuities. So how will this denominator factor? I'll start it out for you. X and x. Now what?
X minus 5 plus 2.
Right, x minus 5 and x plus 2. Everybody good with that? Okay. What two values will make this denominator equal to 0? Yep. So it's discontinuous US at, well, I forgot my S. It's discontinuous at x equal 5 and at x equal -2. And I'm writing them on different lines like this on purpose. We're going to write some stuff next to them. Okay, so because I have two discontinuities, I have the ability to have two possible things happening. They could both be removable. They could both be non-removable, or I could have one of each. Right? How do I decide? Well, I actually take a look back at the function and see what reduces. So if you look from the numerator to the denominator, something will cancel out, right? What is it? Yeah. And when we have something canceling out like that, that creates a hole. So the x equal -2 is actually a removable discontinuity. And we're going to write it a note to ourselves too. This is because there's a hole there. The one that doesn't cancel out creates an asymptote, so it would be a non-removable discontinuity. And again, it's because there's an asymptote. Is that okay? So what this is really boiling down to is being able to factor things, being able to identify asymptotes, and if something doesn't factor, looking at a graph to figure out what's happening at particular x values where I see discontinuities. All right, so let's go back again to our definition of limit and continue that idea. The existence of a limit. So let f be a function, and let c and l be real numbers. The limit of f of x as x approaches c is L if and only if the limit as x approaches c from the left of f of x is L and the limit as x approaches c from the right of f of x is L. And I'll just draw the image that this is describing. It's sort of worst case scenario. If I approach from the left, I get to this hole. And if I approach from the right-hand side, I get to the same hole. That hole is representing my limiting value there. So I have a limit. Now, it doesn't mean that it's continuous, right? I can still have the hole and I can still have a limit. But in order to have a limit, I actually have to be approaching from the left-hand side and the right-hand side in the same way, which we've already talked about that. But we're going to use that fact here in a moment on the next example. So is that definition okay? Should feel familiar. This is not the first time we've encountered it from this intuitive sense. Okay, so we're going to find a constant a such that the function is continuous on the entire line. I'm going to just sort of sketch what's going on here as a general statement. The 3x squared is obviously a parabola, right? And ax minus 4, if a is a constant, is clearly a line. So we have some of the graph being a parabola and some of the graph being a line, and it changes its definition at x equal 1. So it's going to look 3x squared is also opening upward, right? So it's going to look something like this, and there's going to be a break, and then there's going to be a line, and the line has, we don't know if it's a positive or negative slope, will either go down from here, and it needs to connect in order for it to be continuous, right? Or maybe it goes up from here, and it needs to connect. And we've got to figure out what number it needs to be in order for that connection to happen. Does that make sense? Because just like you saw me sort of moving it around, the line might look like that and it would be discontinuous, but we don't want that. We want it to connect at that particular point. Okay? So how do we get that to happen? Well, we use this definition on the previous slide to make that happen. We want to make sure that the limit from each side of the value 1, because the 1 is the location where it's changing, functions, right? We want to make sure that 1 from the left and 1 from the right actually have the same y value. That's going to create a limit at the particular point existing. So we want to find the limit as x approaches 1 from the left and the limit as x approaches 1 from the right. We just need to make sure we're on the right function. So if it's 1 from the left, which of these two parts of the piecewise function am I on? The top one or the bottom one? The bottom. So the bottom one says x is less than 1, right? So from the left means less than 1. So I'm looking at this one in regard to the ax minus 4. And then the limit as x approaches 1 from the right would be the top function, or the top piece of our function, 3x squared. Well, the things that we've been learning in section 1.3 and afterwards are that if we want, and we do have limits existing, we're able to evaluate them at the value 1. And this section, 1.4, is where we said it doesn't even matter if it's a 1 plus or a 1 minus. I can still put 1 in as long as it doesn't create like an asymptote issue or something like that as 0 in denominators. And I don't know how many denominators here. So I'm able to take the value of 1 and I'm able to evaluate it into these functions. So this first one is just a minus 4. And on the second one, if I plug in the number 1, I get what? 3, right? And what I want is I want these two things to be equal. Well, what would a have to be to make that work? 7. So I need the 3 to equal a minus 4, and that means that a would have to equal 7 to make that work. Is everybody good with that? I want to walk you through looking at your calculator for this anyway, just so you can see without any super fancy techniques or tricks or anything, just so you have a way to confirm that this makes sense. So just inside of y1, you can put the first equation, 3x squared. And inside of y2, you can put your new equation that has the 7 in it, so it's 7x minus 4. Now, it's going to look like one of them is going to be, an asymptote, or one of them is going to be a parabola and one of them is going to be a line. And that's fine, but we're concerned with what happens as we sort of piece it together from the left to the right. So 3x squared and 7x minus 4. And if you just put it in a standard window that zooms 6, you'll see the basic graph. So if you don't have your calculator with you, I'll just sketch for you what mine basically shows me, so you have some perspective of that. So this is a very narrow parabola, and then we have a line, I'll do it in a different color, and it's very steep, and it looks like this. And in fact, on your calculator screen, it's almost indistinguishable, the line from the parabola when they're really close together, which is good. That means you're at least in the right ballpark. If they weren't touching, that would be a problem. And if you're concerned or you don't know for sure if it's going to work, you can actually check and see what happens at 1. And you can do that from a numerical standpoint if you want, right? Just put in the numbers like 1.9, 1.99, 1.999, 2.1, 2.01, 2.001. You can do that, and they will pair up to being the same y value, 3. Or you can look at it from a graphical standpoint and just trace along your curve too. So if you trace along this curve to the left, from the left, and if you trace along this curve from the right, you both approach at this point the same location, and it's actually the value of 3. So you can confirm graphically that what you did makes sense. Does that make sense? And if you don't like the graph, just don't do it, but it is another option. Okay. Definition of continuity on a closed interval. So a function f of is continuous on the closed interval AB, the brackets means includes the endpoints, when f is continuous on the open interval AB, and we have these additional considerations about what happens on the endpoints. So the limit as x approaches a from the right of f of x is f of a, the limit as x approaches b from the left of f of x is f of b. What this is doing is it's eliminating the ability that there's asymptotes on the edges of the graph, right? It actually has to be a number value there when you get to the corners of your interval. The function is continuous from the right at A, continuous from the left at B. So what we've had before is we've had continuity on an interval. That was earlier in this lesson. We did that last week. And what that had said is, hey, let's look at this sort of open interval. And if I'm able to, connect everything within the interval, it's continuous. Well, this says I can make it a little bit stronger and make it a closed interval if there's actually endpoint values that to be had, and they don't, go up to infinity or down to negative infinity on those edges. That's all this is saying. All right, more properties of continuity. They're going to feel a lot like our properties of limits since continuity and limits are so intertwined. If b is a real number and f and g are continuous at x equals c, then the functions listed below are also continuous at c. Scalar multiples. Clearly, if you have something that's continuous and you multiply it by 5, that shouldn't change their continuity. Okay? Sum or difference. If you add two continuous functions or you subtract two continuous functions, you still get a continuous function. Product. If you multiply two continuous functions, you will still have a continuous function. Quotient is the only one that might kind of go awry, and it might go awry if the denominator is 0, so there's that condition and they're written that way. It will be continuous, f divided by g, as long as g is not 0. Right? G of c is not 0. Or you can say it's continuous at every location where g of c is not 0. That's another way to phrase that. Okay. We get all of them almost for free because they're just relying back on the exact same properties that had to do with limits. And when we did the limits, these properties were all there. Right? Okay, the next thing that we're going to do is the part that's for your written work. Okay, so make yourself a note. What we're encountering next is the two written work problems processes. So this is called the intermediate value theorem. Intermediate value theorem says if f is continuous on the closed interval ab, and the endpoints don't match, f of a does not equal f of b, so one is greater than the other one. And k is a number between f of a and f of b. I'll draw a picture in a sec. Then there's at least one number c in ab such that f of c is equal to k. So I'm going to mark my interval from a to b. It doesn't matter whether the graph is lower at f of a or higher at f of a. I'm just going to do it like this. Let's see if I can get it drawn in right. So we're saying at a, we're at f of a, and at b, we're at f of b. And k is some value that's in between. I don't even need it to be perfectly in between. It's just somewhere in between those. What this is saying is that there's no way to get from this point at A to this point at B without crossing through K. Right? I can't just skip over it. I can't connect these two and skip over the location where we're actually equal to K. And I can't because it's continuous. There has to be some location. I'll draw this a little bit better so that it will be easier to mark. There has to be some location where I pass through that height of K. And that location down here on the x-axis is what they're calling C. So this is C. So there will be a point between A and C that has the height of K for every height in between f of A and f of B. And it could be more than one. I might have something that's like waving, like a sine curve or a parabola or something like that in between here, right? And it actually crosses this level plane at K twice or 3 times. But we're guaranteed it will at least cross it once. Okay, is that all right? So let's see how we use that with the problems that we're going to be looking at. So we're going to verify that the intermediate value theorem applies. What that's talking about is that it has to satisfy the conditions. What were the conditions? Well, the endpoints are the same. That's one of the conditions. And that K is between f of A and f of B. Those are the conditions. And then we want to show that there then is at least one number C between them, or we are guaranteed that there's at least one number between them that will satisfy that f of C equals K. And we actually will be able to find it. Okay, so our function's a parabola. Parabolas are continuous, right? Yeah, we've talked about that. Parabolas, rational functions, lots of things are continuous. This one's continuous. We have an interval from 2 to 3 that we're looking at. So we're going to start there. So we need to first check that f of 2 and f of 3 are not equal to one another. Okay, so what is f of 2? In other words, what is 2 squared minus 7? Negative 3. And then what is f of 3? 3 squared minus 7? 2. Okay, everybody good so far? They're not equal, right? What would happen if they were equal? Then we couldn't use the intermediate value theorem. That's just it. If they weren't equal, it wouldn't work to use this. That's not going to happen here because it does say verify. It's telling you it's going to happen by the way it's worded. It's not saying check it, see if it works. They're verifying that it does, okay? So these are not equal, so we're going to state that. They're not equal. The other condition over here is that it was continuous. I didn't mark that one. We do need to verify that part as well. I verbally verified it already. So this is really like step 2. Sorry, I skipped it. Step 1 is to write down that it's a parabola, so it's going to be continuous. So f of x is continuous because it's a parabola, or you could say it's a quadratic, or you could say it's a polynomial. Any of those things would be fine. Okay, it's continuous. The endpoints don't match. And then step 3 needs to verify that the the k value that it gives us is in between the two endpoint values that we're looking at from the y value perspective. So the value of 1 really is between negative 3 and 2. Yes? Yeah, it is. So we want to make sure that we verify that that piece is there too. So these are the 3 verification steps. So in your homework, written homework, every single problem, there's only 2 problems, but you're going to verify all 3 of these things. The function's continuous, the endpoints don't match, and the k value that it gave us is between the endpoint y values, f of a and f of b. So once we've verified that, it says we can apply the theorem and we can find the value of c. So we're going to write down, so the intermediate value theorem, I'll abbreviate IVT, the intermediate value theorem applies. And it means that my function, which was x squared minus 7, will equal 1 somewhere between x equal to 2 and x equal to 3. And we're going to be able to solve this. And you know how to solve this, at least you have at some point in your past. What do you do next? Add 7. So I have x squared equal 8, then what? Square root both sides. Technically, when we put square roots on, we get a positive or a negative. I'm going to write it here for the moment, but I'm going to say that the both of the negative and the positive don't have to be between 2 and 3. Just one of them needs to. So the negative is actually not going to be the c value I care about, but it does satisfy this equation, right? Square root of 8. How does that simplify? Good. 2 square root of 2. So we have 2 possible values. We have x equals 2 square root 2, and we have x equals negative 2 square root 2. This one is not the one we want because it's outside the interval 2, 3. Right? It's negative. So this is not the c value I'm looking for. And if you want to verify that this 2 square root of 2 really is, grab your calculator and just type in 2 square root of 2, or you can type in square root of 8. What is the approximation for this value in decimals? Just, what is it? 2.83. Is 2.83-ish between 2 and 3? Yeah, it is. So it's the one that satisfies the conditions, or the ending part of our theorem. So this value is c. So c is actually 2 square root 2. C is not 2.83. This is our benefit, like sort of visually speaking, we want to verify it in our mind that that really satisfies it. So we're sort of checking it ourselves on an approximation, but the exact answer is still 2 square root of 2. Okay, any questions? Okay, so written work should be at the bottom of your paper. If you haven't printed those off, let me write it here. You have WebAssign, but you also have, I think I do have it. It's page 83, numbers 96 and 97. Just 2 problems, and they'll be like this.